We are ready to practice counting electrons using the neutral method I taught in lecture 1. I suggest that you practice this before you listen to this lecture, so pause, count through it. The two possibilities are I'm going to give you a structure which gives you a little bit more information, or I may just give you a formula. And I will go through this rather quickly. I'm going to highlight some of the ligands like, you know, EC or CR, the ones that I think that need a little bit more explanation, but I suggest you do it again by yourself before you watch. And then at the very end I'm going to introduce a new rule for carbonyl clusters, and then we're done with this chapter. Alright, so ferrocene, you want to start, it's a neutral complex, you add up all of the metal electrons. Just as a reminder, you find iron, you count the S and the P electrons, so iron has 8 valence electrons or electrons available for bonding, so iron is 8 electrons, and then each of these is an eta 5 Cp minus, which donates 5 electrons, so you write 2 times Cp minus, which is 10 electrons, to give me an overall count of 18. So eta 5 tells me two things. It tells me it's 5 electrons. It also tells me that it is a negative charge, which is irrelevant in this case, but it might become important if we are counting or if we are looking at the oxidation state of iron, which is not a problem at this point. Looking at chromium here, go find chromium. That's 6. So chromium has 6. The carbonyl ligand, that's easy to spot. Carbon monoxide, 2 times carbonyl, sorry, it's 4, each of them 2 electrons, so that's 2. The I must be negatively charged, so this is I minus, monoanionic 1 electron donor. And then if you wish, if you're uncertain about this CR, so there's a single R group, which means we are missing 3, so we've got 3 connected most likely, so that's going to be 3 electron, right? Remember, we pull this in half, and so you get 3 electrons for this RC3, and then if you add it all up, you get 18 electrons. So you see 18 electrons and 18 electrons. You can't always count on it, as we will see for the next one, but if you're uncertain, I would take a guess and add up to 18. Obviously, I'm going to have some different ones here. So nickel is, and I'll show you, I'll go at nickel one more time here, right? So this is group 10, 8 D electrons, 2 S electrons, that's 10 total. I won't show the periodic table again for the next slide. I'll just write it down. It's not that difficult to determine. So nickel has 10 electrons, then we have 2 times the carbonyl, which is 4 electrons, and COD was cyclooctadiene, so we can get up to 4 electrons. We can have an eta 2 or an eta 4, that's up to you to decide. In this case we need 4 more, so it's ideal to just say eta 4 COD, and this is important that you indicate that to me for full credit, and so that again gives me 18 valence. No, electrons are 18. I don't know why I keep calling them valence electrons. They're simply 18 electrons. So here, if you see something like EC, you have access to the notes, you have access to the internet. You can determine what that is on the go. Platinum is 10 electrons, so we have platinum has 10 electrons. Pick out what you know. The amine is a neutral 2 electron donor. The chloride or chloro is a monoanionic 1 electron donor. So we have the amine, 2 electrons. We have the chloride, 1 electrons, and then EC is either going to be 3 or 5, right? Because this adds up to 14. So it's 13. So if we get 3, we have a 16 electron donor. If we get get 5, we have 18, so ideally it would be 8. You'd be wrong. ACAC is acetyl-acetonato, which is pentane dione originally, and then when you deprotonate, it gets a negative charge, so it's going to chelate and make a 5-membered ring like this. So one way to look at it is you have this negative charge, so you have a mono-NS, can delocalize if you wish, and you can have a monoanionic contact, 1 electron donor, and then a neutral 2 electron donor, but it's overall 3 electrons, so the ACAC is 3 electrons, which gives us a 16 electron species. This one is pretty easy. The thing that we're introducing here is the counter ion, so this complex has an overall 2- charge. These aren't counted, and so we'd simply add 2 electrons to the total electron count and ignore any kind of charges on the counter ions. So iron is 8 electrons. 4 times, again, the carbonyl, this is getting old, is 8 electrons. 2 times monoanionic chloride, and then you have to do the charge, which is also 2 electrons. So this is actually a 20 electron species. Let's do this chromium cation complex here. Chromium has 6 electrons. Each aqua ligand, which we have 6 of, is a neutral 2 electron donor, so that's 6 times 2, which is going to be 12 electrons. So let me write it over here. So that would be 18, except we have to subtract 2 electrons for the charge. Oopsie. So minus 2 electrons, which ends up being a 16 electron species. Let's do ruthenium down here first. So ruthenium has 8 electrons. It's in the iron group. N2 is just dinitrogen, so we consider that a neutral 2 electron donor. So N2 is 2 electron donor. So are the amines. So we have 5 times NH3, which is 2 electrons each. So that's 10. So, and then that would be 20, but we have a charge. So this doesn't line up very well. But we also have the charge, which is 2 electrons. We subtract them, so we end up with 18 electron species. Let's look at this cobalt one. Cobalt is in group 9, so cobalt times 9 equals 9 electrons. We have ethylene diamine, which is a neutral chelating ligand, so that's 2 electrons per contact. This is something you should remember or know without looking up. It's a pretty common ion. Sorry, it's not an ion. Chelating ligand. So we have 2 times 4, right? That's 8 electrons. Then we have this NO2. So NO2 is monoanionic. So 1 times 1 electron. It does have the possibility to chelate, right? So it could be a 3 electron donor. We don't know. We also don't know whether it coordinates through nitrogen or through oxygen. So, but it's technically it can be 4. Let's see what we have without it. I wrote 1 already, but so we have the chloride, monoanionic, and then we have a charge, which is negatively has a negative charge. So we have 18, we have 19 electrons. So it's highly unlikely that this is a 3 electron donor. So we're going to go for 1, which makes this a 20 electron species. So like I said, you can have 20, 19, 18, 14. You can't count on it. So now I'm giving you a structure. And so you just need to kind of look at what you have and add up everything step by step. Ruthenium is in the iron group, so ruthenium has 8 electrons. Then the easy ones are the chloroligands. They are monoanionic, so 2 times Cl-, which is 2 electrons. The phosphine here, tricyclohexylphosphine or cyclohexylphosphine, well, it doesn't matter, 3 alkyl groups. So R3P, which is 2 electrons. So we're up to 12 now. We're going to stay away from this for now because we can do the carbene. That one is not that hard. It's just like that glorious catalyst for the Suzuki coupling that we've seen. So this is a carbene. So R2C, 2 electron donors. And then so we have a carbon here and we show a double bond, but because there's an angle, there has got to be a hydrogen here, otherwise it would be shown linear, and then we would look at it as a different donator or donation group. But this is definitely a carbene, so we have another carbene here with 2 electrons, and when we add all that up, we get a 16 electron species. This one, obviously I'm using this benzene-like ligand as the one variable here, because osmium is easy. We just look it up. It's in the iron group. Is it? Yes. Triphenylphosphine is a neutral 2 electron donor. We have 2 of them, so 2 times, that makes it 4. We have 2 chloroligands again, so 2 times that. We have a charge, so charge, we subtract an electron. If you add all that up, that's 12, 14, that's 13. So if we could get 5 electrons out of that, it would be 18 electron species. That's going to be kind of tough to do, but what you need to do is look at each of these contacts separately to come up with the overall charge. And so what's missing is, of course, the groups here. This is just like a benzene group. So each of these carbons does have a hydrogen, and once you figure that out, you can argue that, okay, we have 2 groups here. So this is a carbene-like interaction, or 2 electrons, but this one is more because it has a double bond away from the metal, so this is more like an alkyl group. So this is the monoanionic 1 electron donor, so you get 1 electron here, which makes this an overall 3 electron ligand. So this would be a 16 electron species. Iridium is in the cobalt group, cobalt, rhodium, and iridium. So there are 9 electrons. Each of these phosphorus contacts has 3 groups, so they're all phosphines. So that's 2 electrons and 2 electrons. The hydrogens are hydride, so those are monoanionic, 1 electron, 1 electron, 1 electron, and 1 electron. If we add that up, 9 plus 4 for the hydrates plus 4, that's 8, that's 17. So we really need 1 electron. So this could be a carbene, a 2 electron donor. We have 2 groups here, but that would make it 19, which is possible but unusual. So it is also possible that there is a hydrogen that's not shown. Not a new thing. It's not like these 2 hydrogens are shown or these 2. We leave them out. And so this is most likely an alkyl group or a 1 electron donor here. So this is another good one where you might have to analyze, and it helps to have the structure. Here are a couple of examples that students found in the chemical literature. These, I believe, are from 2023 spring semester, so they're fairly current. And you don't always get a clear picture because sometimes the structure shown in the graphical content of the paper are incomplete, and you have to go to the actual paper, and you don't always have access to that. So let's just keep that in mind as we put these puzzle pieces together. So we start, so obviously the interesting part is this ligand here. It looks like it's the methane molecule that somehow is binding, and so it doesn't have a lone pair of electrons. It's not charged. If anything, it would be the sigma bond here that does any kind of donating, and so that's a possibility, as we know from the boranes that I showed. But let's just see what we need. So if osmium is of course, in the iron group, that's 8 electrons. Both of these are phosphines, so we have 2 times phosphine, that would be 4 electrons. And we know this is a cyclopentadiene, so eta 5, terrible eta, which is Cp minus, or 5 electrons. And so I'm going to assume that this charge is the overall charge of this complex. So I will subtract this right here, which brings us to 16 electrons. Let's make sure 4, 12, and 4. That's 16 electrons, and so it would make sense that this 2 electron or 3 center 2 electron bond would be a 2 electron donor, or this CH4, and then that's most likely what it is. These interactions between these hydrogens are called agostic hydrogens. So you can actually have an interaction like that. It's called the agostic hydrogen. So that's how I would do it, and based on the limited information that I have. This one here is not as tough as it looks. The only thing that you need to figure out is what the charge of this complex is, and so the PF6 ion would have a negative charge. So each of these has a negative charge, which means there's a 2+ charge here, right? If you don't know, you can actually draw that structure. All right, so you have hexafluoro, and these fluorines are going to be all terminal, all formal charge is 0, and since phosphorus has 5 valence electrons and 6 bonds, it's probably going to be a negative, no, it is going to be a -1 charge. And so that's how we know that. Iron, of course, is 8. And then we look at each of these ligands here. We have 2 of these chelating ligands. This end here is an amine. So we have that's 2 electrons for the amine contact. So NH or NR3 amine contact. And then this is a carbene contact. So that's another 2 electrons. So there would be 4 electrons per chelating ligand. We have 2 of them, so I'm going to write them separately here. We have, let's do the 2 amine contacts and 2 R2C carbene complexes, but it's really the chelating ligand has an amine and a carbene function. And then we have the charge, and so we have a +2 charge, so we subtract 2 electrons, so we actually are at a 14. Wait, I forgot the cyanide ligands here. So those are in acetonitrile groups, so you need to know that we have a carbon triple bond here. And so those are 2 electron donors. That's going to make a heck of a lot more sense, because that adds 4 electrons for those acetonitrile groups. And so that makes that an 18 electron complex. So that's enough practice. I have a few slides where I'm showing structures. Feel free to pause and practice. I'm not going to go through any of them. If you're in my class, you have access to the slides. There's only one last thing that I want to show you. So here's another one you can have fun with, and another one, and another one, and another one, and this one here. And some of them look scary, but they're really not. You just do one contact at a time, and before you know it, it might make more sense than you think. And then here's another one. So you have plenty of 18 electron rule practices. And so the last thing I want to show you are metal-metal bonds and what they do, and specifically look at metal carbonyl clusters. If we look at this pentacarbonyl manganese compound here, and we count electron, so manganese is 7 electrons, and the carbonyl, which is neutral, would be 10. We end up with a 17 electron species. So if we make a metal-metal bond and we treat it just like we would any covalent bond, that by sharing an electron, each metal center gains an electron. We would have a metal-metal bond, which adds an electron, and so that would be, oh, that's convenient, 18 electron species. So what this says is it's that each metal gains 1 electron per metal-metal bond, and so that happens. And so these metal carbonyls are going to form clusters and dimers, so that every single osmium, or in this case osmium, every single metal center will have 18 electrons, and it'll do that until it has that. Just back to metal-metal bonds. So if we count rhenium here, rhenium has 7. So I'm going to do this for each rhenium center. Rhenium has 7. We have 4 chloros, and so then we have 1, 2, 3, 4 metal bonds. That gives me 4 electrons, and then I have a -2 charge, so I add an electron for the charge. It's just 1 electron because I'm looking at it. I'll cut it in half. It's symmetrical, and so when I add that up, I get 8 and 8, so that's 16 electrons. The 18 carbonyl cluster rule only applies to carbonyls. This is not a carbonyl cluster, but over here for this osmium, this should work. You can look at, and you should count for each osmium. This is, again, it's symmetrical. Each of these osmium metal centers has 3 terminal carbonyls. Each carbonyl is 2 electrons, so 4 times 2 is 8. The osmium itself is also 8, and then we have, it's not 3 metal-metal bonds, it's 2 metal-metal bonds. So 2 metal-metal bonds gives me 4 electrons, and so that would be an overall 18 electron complex. So all this, also bridging carbonyls are going to, obviously, if we have 2 electrons and we split them between 2, we attribute 1 electron per metal center. And so if it's symmetrical, again, you can just count individually, and if it's not, you want to count the iron up, do 8, 3 times the carbonyl, which is 6, then a metal-metal bond, which is 1, and then 3, we call them mu COs, that would be 3 electrons, and then you get to your 18 electrons. This way, if I give you a formula, if I give you a formula, let's say, and ask you to predict the shape, or molecular shape that you want to work this backwards. So no matter what your metal is, you always start by taking the number of metals times 18, which gives you the number of electrons total required for this cluster. So we're after 72 electrons, and then you subtract out how many electrons we have from the carbonyls and from the metals. So if you look up rhodium, it has 9 electrons, you get 36. You subtract that from the 72. You also have 12 carbonyls, so that's 24. And when you subtract all of that, so you have 72 electrons needed. We had 36 from rhodium, and then we're also subtracting 24, so that's 50 total. So 72 minus 50 gives me 12 electrons. So those are the missing 12 electrons, and so we need to get 12 electrons from metal-metal bonds. And so if I simply divide that number by 2, I end up with 6 metal-metal bonds. So I know that somehow there have to be 6 metal-metal bonds. And if you distribute them, I didn't realize I had that written out here nicely, 12 missing electrons, which means 6 metal-metal bonds. And so you, in this case, you have 1, 2, 3, 4, 5, 6. You try to make this as symmetrical as possible. Sometimes it's not as possible. But so now if you look at each rhodium, we have 9 plus 3 for the metal-metal bonds. That's 12, which means each of these rhodium needs 3 carbonyls. So 1, 2, 3, 1. Okay, 2, 3, and that adds up exactly to the missing number. Now the reality is that some of these are going to do bridging, and then but you don't need to as you draw these. For me, bridge them if you want. That's fine. So this is what this could look like. This is one of the possibilities, as long as every rhodium center has 18 electrons. I will accept that structure, use the method I've shown you, and here are some. These page numbers may no longer correspond. I didn't verify that, but the Shriver-Atkins book has a section on carbonyl clusters. You can go to it, look at some of the examples, and so definitely focus on the ones that are simple metal carbonyls. All right, that's the end of chapter 7. We'll have a big exam, and then we'll do some nuclear magnetic resonance stuff when we're done with exam 2.